All right, good morning. We are going to do lesson 6.7, which is called staking it. And today is just more of what we've been doing, but now we're going to do it in more of a generic sense and see if there's any shortcuts that we can make. So the very first thing is by the end of today, you'll be able to calculate arc length for angles of rotation measured in radians. Visualize size of angles measured in radians, including radians given in decimal form. You'll be able to answer how large is a radian, how can I estimate the size of angles measured in radians relative to degrees, and what good are radians? Are any calculations made easier when angles are measured in radians, and are any contexts made easier in when you're describing that? So I've already kind of talked about why I like radians better, and at first I'm going to tell you the transition seems a little funky. Like, why do we have to have two sets of measurements? But all these questions that they're asking here will help highlight what the 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 idea of it. She's right. Okay. So the next one. So I want you to read this context, and I'm just gonna have you pause it, just so that you can read it on your own. Because when I read through it, I'm going to kind of read quickly because I already know what I'm doing. I'm not reading it so that you'll understand, because you're going to understand it on your own. Okay, so now that you've read it, I'm going to read it to you. So it says, after considering different plans for laying out the archaeological site, describing and digging it, Alice, Javier, and Veronica have decided to make a concentric circle at 10 meters intervals from the center tower. So again, the reminder of concentric circles looks like this. So this word here is the target symbol, where you have circles that have the same center. So circles with the same center. So they also have decided to use 16 stakes. Now we've used, 10. We've split a circle up into 10 with the Ferris wheel and even 12. And now we're doing it into 16. So remember what you did with that 10 and that 12 with the Ferris wheel. This is a similar thing that you're doing here. We're just switching out numbers. So in order to have a few more points of reference, so using ropes of different lengths to keep the radius constant, they've traced out as circles in the sand, um, because they know that circles will soon be worn away by the wind and by people's footprints. They feel a sense of urgency to locate the points um, of, of the 16 stakes that will make each circle. The team wants to be efficient and make as few measurements as possible. So here we have Veronica, and it says Veronica suggests that they should locate the stakes around one circle. Oh, I just realized I'm on the wrong page. Sorry, give me 1 second. I'm not taking notes on the right page. There you go. Okay, so let's go. So Veronica suggests that they should locate the stakes around one circle and use those points to mark the stakes, and that will go on all the circles. And what do you think about Veronica's idea? So she's basically saying this: if you have a circle, right? If you have this circle kind of like this, and forgive my circle, and then here's the tower, and they say, okay, well, here's the first stake. They can like draw these lines like this kind of thing. And then because we know one's going to go here, for every single circle, it's going to go like that. And then the same thing goes for your next, kind of ones like this. They're just going to meet wherever those circles are and wherever those lines meet. Does that make sense? So imagine these concentric circles. We have another circle like this. Okay. So I'm in the hotel lobby, so if you hear noise in the background, you're welcome. Okay, so how will making stakes on one circle help them locate the position on the other? So go ahead and describe that for yourself. Make sure you write your answers here. I am looking for your answers and for you guys to be filling those out. Okay, so the next one go ahead and fill that out, pause the video, and do what you need to do. For this next one, so now that you've filled that out, what they're really looking for is how will making stake positions on one circle help them locate the positions on the next circle? And it's exactly that. Okay, so it's exactly this picture that I showed you here. So can you imagine like really wonderful, perfect circles? And then we have these kind of like lines going out from the center, and those would be your radius, right? Your radii. And wherever the circle intersects these lines, that's what we're actually looking at. So over here it says, if there are 16 stakes per circle, how far apart are the stakes in degrees? And so I don't know if you saw my notes from earlier and got my hints from earlier, but the way it works is that you're going to take, so it says how far apart are the stakes in degrees. And so if you think about this, they're thinking about degrees per stake. Okay, sorry, I had to take a break real quick. Okay, so just like it says stakes in degrees. So that's how many degrees are in each stake. That's all they're asking. So how many degrees are there in a circle? And you're like, oh, there's 360. And how many stakes are there? Oh, that's 16. And so we get, and I have to use my calculator because I don't have the answer right in front of me. So 360 divided by 16 is 22.5. So we get 22.5 what? This is degrees per stake. Like, does that make sense? So from here to here, you've traveled 22.5 degrees. Does that make sense? All right, moving on. So how far apart are the degrees, the stakes in radians? Okay, how far apart are the stakes in radians? Now remember that in order to find things in radians, you're going to use the arc length. So we're going to go arc length divided by your radius. So our arc length in this case is going to be, let's see. So we got, what was the meter? What was the radius again, guys? I think our radius was 50, but I can't remember. Let's see. 10 meter intervals, 16. All right, so here we go. So it's going to be 1/16, right? Because we have 16 stakes. We only want 1/16 of them. And then we're going to multiply that by 2 pi times 50. And then we're going to divide it by our radius, which is 50. Okay? So then if you notice, these 50s will divide out. And then so we get 2 pi over 16, which is just pi over 8. So we're dealing with a circle or a triangle that has a radian measure of pi over 8, or in terms of degrees, 22.5 degrees. Okay. So then it says Veronica has decided they should stake out the circle with a radius of 50. That's what we just found out, right? She is standing at the point of 50, 0 and knows that she needs to move 22.5 degrees all the way around the circle to place her next stake. But she wonders, how far is that? So one more time. Veronica has decided that she should stake out the circle with a radius of 50 meters first, right? So can you think about that circle in your head? Right? So think about that circle right here, and then you have this, and this is 50 meters, right? And so she's going to set those 16 stakes, right? So my brain always goes to like cutting things in half. So there's 2, and then here's 4, and then cutting those in half and half and half. So you can kind of imagine like there'd be a half here. So now that's 8, and then half again. So that's now 16. I'm just cutting everything in half, and then that's how we would get all of our 16 pretty evenly, right? Not perfect with that circle is kind of lopsided, but that's okay. Okay, so it says she is standing at the 50, 0 and knows she needs to move 22.5 degrees around the circle to place her next stake, but she wonders how far is that. Veronica decides that she will find the distance by setting up a proportion using degrees measurements. So a proportion, if you remember what a proportion is, it's what you learned in 7th grade, where you're taking a part of something. So half of something, a fourth of something. That's basically what you did up here with this 1/16 business, right? Okay. So then it says Alice thinks, so that's Veronica's strategy. So I'm going to pause right there and work out Veronica's strategy really quick with you. So she's going to proportion it out in degree measurements. So whenever you're proportioning stuff out, you think about what you want versus what you have, right? So we want 22.5 degrees, and we have 360 degrees in a circle, right? And then we are gonna set that equal to our proportion, right? So what proportion are we using? Let's see here. Let's see. Hold on a second. Let me wait till this lady passes. Sorry. Equals to so again, she's wondering how far to place her circles. Okay, so then this is going to be the distance that we don't know. We don't know how much that is, divided by our circumference of our circle. And again, circumference is equal to 2 pi r. So that's going to be equal to 2 pi times 50, which is 150, okay? 100. Okay. All right, so then we're just going to solve this proportion. If you don't remember how to solve this, I really like to do multiply by the least common denominators. And so that's what I'm going to do right here. However you want to do it. Some people cross multiply. So I'm going to, actually, I will cross multiply. So I multiply and I get, let me just write this in a different color. So I would get 2,250 pi equals to 360 degrees times d, and then I will divide by 360, and then so whatever that is, right? I'm just gonna let me see if I can scoot this guy over really quick. There you go. So then this turns into, and then I'm just gonna bring up my calculator because that's just easier. So here we have so D is equal to 2,250 pi divided by 360, right? And then, let's see, 2250 pi divided by 360. Hey, Ms. Johnson, do I have to hit degrees? It doesn't matter because these are proportions, so all your kind of stuff goes away. So this is about 19.6 meters. Are we in meters? Yeah, we're in meters. Okay, moving on. Alice's strategy is, Alice thinks that they should find the distance by taking 1/16 of the circumference. So we just calculated the circumference at 100 pi. So her strategy is just going to be like 1/16 times your circumference, which is 1/16 times 100 pi. So that's going to be equivalent to, so we're going to go 1 divided by 16 times 100 pi. And wow, I get the same answer, right? No surprise there. So oops. And then so my math brain says, "Hey, why are those the same answers but the calculations are different?" So let's just like take a second. Do you see any parts of um, this? Let's see, of this formula here and this formula here. Do you see anything that is similar? Do you see anything that you're like, oh, I see it's the same thing? So yeah, for sure, you see that the 100 pi right here, you see this 100 pi and this 100 pi. Hold on, guys. Okay, so we're back, guys. Can't organize myself. Sorry, they started vacuuming. Okay, so your job is to figure out how these all are connected, right? So where do you see that 100 pi? Oh, I see it right there. Do you see the 1 over 16? Do you see that anywhere? And you should, because you should remember that back up here, the way we got 22.5 was we divided by 16. So the way we do this is that 22.5, right, is 1/16 of 360. So this fraction here is the same as this fraction here. Does that make sense? So really, are their strategies different? Yes. But do they come up with the same answer? Yes. Okay. So lastly, Javier thinks that they should use radian measurement in their calculation. So the radian measurement that we got up here was pi over 8. Does that make sense? Okay. Sorry, I lost my little thing here. So we are also going to use that, right? And so when we get pi over 8, so we're going to use the formula S equals to r theta. This guy, in case you don't remember him from before, this is arc length. So this is like if you're wondering about a little ant and he's walking around a circle track, how far did he walk? So how long is that piece of circle that he walked? So you multiply the radius times the angle, right? And so that theta is going to be very interesting. So we know that theta equals, if I solve that for theta, it would be equal to S over R, which is in this case, we know that um, the the S in this case is going to be your circumference, right? So that's going to be, let's see, 50 times 2R, because that's your circumference, which we already know is 100 pi, divided by 16, which is 100 pi divided by 16, which again is about 19.6 meters. Again, do you see your 100 pi? And everyone's like, yeah, Miss Johnson, I see it right there. Yes, you do. And then do you see that 1/16th? And you're like, well, I don't see 1/16th, but I do see dividing by 16, which is exactly the same, right? All right, let's move on. So it says Javier has a different idea. He suggests that they should figure out the locations of all the stakes in the quadrant one first, and then it would be easier to find the locations of the stakes in all other quadrants by using quadrant one locations. And this is a strategy that some of you came up with. I saw in some of your homework and some of your explanations of different pieces. And instead of you finding every single one, I think I have a circle here. Instead of you finding the whole circle, you found quadrant one and then you reflected those numbers back, down, left, right, across, whatever you did. Right. So that's where Javier's strategy is coming in. Some of you already figured out. So good job for you. So do you think Javier's suggestion would work? Actually, some of you already know that it'll work. For those of you who didn't use this strategy, just know that in a circle, there's many, many lines of symmetry, meaning I can fold it in half and it looks like a semicircle. I can fold it again and it looks like a quarter circle. And I can fold it again and it looks like a piece of pie. And I can fold it again and it looks like an even skinnier piece of pie. So that's all they're reflecting on there. Okay. Go ahead and read this next part, and then I'm going to read it to you. Okay, now that you're back, it says Javier has already started working on his strategy and has completed the calculations for several random points in quadrant one. Alice has a concern. So using x comma y coordinates means that we would have to start at the central tower and go right and then go up, right? And then drive in the stake, right? That's one way to do it. Then they're going to have to go back to the central tower and then start all over again by going right and then going up to where the stake is. So that's what rectangular coordinates are. This is what you guys are used to, your x comma y business, yeah? So if they had to graph a bunch of points, they're always going to have to go back to the center and then they would go, I don't know, let's do like this way to get to one stake, and then they'd have to travel all the way back, and then they have to go this way to get to their next point. So they're always having to go back to the center or the tower, right? Which is not, you know, um, very efficient. So then Veronica says, I have another idea. I want to use the compass to orient the direction that we should walk from the central tower and then drive stakes every 10 meters along that line. Then I can return to the then I can return to the central tower and head off in another direction. And then she says, unfortunately, my compass gives me angles in degrees, and Javier labeled his diagram in radians, so I need to label each point r comma theta. So let me just explain what whose strategy is this. Veronica's strategy is, right? So Veronica's strategy is, let's go here, right? So let's start at the tower and then let's walk, a certain this, right? Along one of these things. And then drive a stake every 10 meters. So that way, do you see the difference between this strategy here and going back and forth here? Do you see that? Do you see that difference? Okay, so that's her strategy. So it says develop a strategy to locate the other stakes in quadrant one for these additional circles. Find the XY coordinates to complete Javier's strategy. Um, the r comma theta. So r is your radius, theta is your angle, and coordinates for Veronica's strategy. And the arc lengths for the positive x axis to each point for Alice's strategy. Okay, so go ahead and think about what a couple of those strategies actually mean. Okay, so it says, now that you've thought about that, and there's a couple different strategies, and there's actually a really slick way to do it too. But we'll talk about that in a little bit. So just know right now, you understanding how, who are the two people? Alice's concern of going back and forth to the center is going to be super annoying, right? But then Veronica's strategy of going along a particular, like one of these, like, walking along this way, right? She doesn't have to go back to the center every single time, but she will have to go back, to get to the next, set of stakes like this, right? Right. Okay. So then next, Javier has noticed that the further away that from the central tower, the further apart the stakes appear to be. Okay. Say what? Okay. So he says the further away or the farther away from the central tower. So pick any point you want. I don't know. Pick this guy right here. Okay. He says the farther apart the stakes seem to be on that circle. Yeah. So he's saying, hey, that looks further. This looks further than if you were to go here to here, right? And he's right, right? It looks right. So he suggests they should add radial lines to the diagram at angles of pi over 16. Now remember that this guy right in here right now is pi over 8. That's the angle pi over 8. So where would pi over 16 be? Where would pi over 16 be? Where would pi over 16 be? Yeah, hopefully you see the relationship. It's half of it. It's half of it. So then, so ignore my bad drawings here, but like imagine another radial line going that way, right? That's what he's suggesting. That green line there. Okay, so then it says, but only locate stakes at these angles on the circle's radius is at 40 meters. So not going through every single one, just going like on this very outer circle here, right? Does that make sense? Okay, so what do these angles measure in degrees? So think about how you would calculate how many degrees that would be. Think about how many degrees that would be. And some of you come up with, there's a lot of different ways, like, right? You can come up with at least several. I mean, look at how many different ways that we came up with for calculating the distance, right? For the 50-meter circle between each stake, right? Okay, so there's going to be a couple different ways. The way that jumps out to me, well, if I already know that it's pi over 8 and I'm cutting that in two, so I'm taking half of that, I'm just going to multiply by that by half. And so now I got pi over 16, right? So I could do the same thing with our degrees, right? So if I already know it's going to be 22 and a half degrees, I'm going to cut that in half, and now I'm going to get 11.25 degrees. So multiply this by half, and I'm going to get 11.25 degrees. Now this guy in here is 11.25 degrees. Okay. And then I could just, if I want to now figure out, okay, so 3 pi over 16, I'm going to write them in green so they stand out for you, right? So then how would you calculate that angle there? How would you calculate the one that I just drew? And again, some of you have several different ways to do it, and you can see that I have 3 sections of it. So I can multiply that by 3. So I can go 3 times 11.25 degrees. And that would be 33.75 degrees. Some other people, I know you guys see this as additive, so you know that the pink angle here, this guy here is 22.5 plus your 11.25, that would give you 33.75, right? So go ahead and calculate the rest of these. I didn't do those two, so go ahead and calculate those. And we're going to move on. So it says, Alice and Veronica love this idea and assign Javier the job of finding out the posts of the 40-meter circle since there will be twice as many of them. Javier realizes he doesn't need to calculate the rectangular coordinates for each point to locate their positions, and he just plans to walk around the circle posting stakes at equal intervals. How far apart are the stakes on the 40-meter circle? Okay, so again, this is something that you should be comfortable with doing. So think about your strategy in terms of doing that. How would you do that? Okay, so now that you're back with me, remember that you can always use your like whatever formula you want. I mean, let's see. Here's 3 different formulas that Javier, Alice, and Veronica used. Javier is probably going to use his same formula, which is very similar to this, right? So he's probably going to do this, which is going to be the circumference. Let me see, is that right? Let me see. Yeah, the circumference of the circle divided by how many, sections they're going to be, right? So he's going to go, oh, wait, this is the wrong circumference because that's the 50-meter circle. Okay. Sorry. So he's going to go with circumference, which is 40 times 2 pi. And then he's going to divide that by how many sections there are, right? So because there's still going to be 16 of them, right? Because he's not going to do, obviously here, he's not going to do let's see, he's not going to do this pink one here and this pink one here because those ones are already done. So it's still divided by 16, right? So I'm going to just divide this by 16. And that's equal to, let's see what that equal to. So we got, let's see, 40 times 2 pi divided by 16 gives us about, hold on a second, that's 15 between the two of them, right? And then we have to divide that by 2, right? Does that make sense? So now we're going to divide that by 2. Is that going to, no, I don't want to do that, sorry. I want to take that and multiply this by 1/2, because now we want to get in between there, right? So this is for the 16, and then we're going to multiply this by 1/2 to get in between those two, and so we get 7.85. Okay, so that's how far he is posting these things, right? It goes here, 7.85, right? All right, moving on. It says being able to convert quickly between degree measurement and radians will help Javier a lot. So develop a strategy that can consistently that you can use consistently to convert angles from degrees to radians and then from radians to degrees. Okay. So one of the things that you should have seen is that we keep bringing in this 2 pi business, and 2 pi helps us in comparison to 360 degrees. So if you want to like convert from degrees to radians, we're going to multiply it by 2 pi over 360. Similarly, for this one, we're just going to multiply by 360 over 2 pi, right? And the reason why in my brain is 2 pi is a circle and so is 360. So when someone says, oh my gosh, he did a really cool 360, they could really say, oh my gosh, he did a really cool 2 pi, right? Because it's a whole circle. So hopefully you kept seeing the 2 pi business. Do you see the 2 pi here? Do you see the, let's see, 2 pi? You should see the 2 pi in all of these strategies as well. Technically, there's a 2 pi in here, a here, and here, because that was 2 pi times your radius. And here you can even see your 360, right? Okay. Lastly, it says Veronica has a different proposal for soon to be added 50-meter circle. She places a stake at every 15 degrees. How would you calculate the arc length between the stakes in your 15-degree computation, and show how to calculate arc length between stakes using the radian measurement? So I'm going to leave this one for you so that you can calculate it and you can practice. Again, you probably want to um, um, how would you calculate the arc length between the stakes? So again, you're going to be using that formula, and you get to pick which formula you liked. Did you like Javier's, Veronica's, or Alice's? And then down here, show how to calculate the arc length between stakes using radian measure, right? So same thing, not new. We are just doing a different circle and a different degree. Okay. We're going to go over our takeaways to make sure that you guys are all set, and then we're done. Okay. So it says, let's see. So if a circle has been divided into n equal arcs, right? Like, remember, we're cutting it up. And if you want to think about what an arc is, that's your pizza crust on the edge of your pizza. Then the angle measure of one arc is going to be how much? Like, what did we do to calculate that 22.5 degrees? Okay, and so hopefully you say 300. Oops, I'm still in that mode. So hopefully you said it's 360 divided by n, where n is the number of arcs, right? So this time we did 360 divided by 16 because there were 16 stakes, right? Before you did 360 divided by 10 because there was 10 sections of that Ferris wheel. Or for radians, now what is 360 degrees? Yeah, that's 2 pi. So this would be 2 pi divided by n. So hopefully that makes sense. So if you haven't learned this yet, you really want to remember that 360 degrees is equal to 2 pi. So please know that, right? That's like something that you should be in your head. And then it says, I can find arc length for an angle of rotation measured in degrees by using the formula. Okay, so this formula is here. I'm going to write it here. So S is equal to, and S is your distance, theta, whichever angle you're talking about, divided by 360 times by 2 pi r. And you should reference that 2 pi r is your circumference. And I'll put a big C there to remind you, oh, that's my circumference. Okay, so we're not coming up with new formulas. We're just taking the proportion of that circle, right? That proportion, half of it, a third of it, 22.5 degrees over 360 of it. Okay. I can find arc length. Oh, sorry. So this one was degrees. We tackled degrees first. So of course we're going to do radians. So you should be able to convert this formula, right? So instead of writing theta over 360, what would you write there, right? And some of you are like, oh, it's 2 pi, Miss Johnson. And then we multiply by 2 pi r, which again, that's your circumference. But if you notice, your 2 pi's cancel. So this is just r theta. Okay, that's just r theta. And that's something that you might remember from integrated 2. I'm not sure if you didn't learn it, that no problem, because now you know it. And lastly, I can convert degrees to radians by multiplying by, what would you multiply by? And this one's multiplied by what? So if I'm going from degrees to radians, I want the degrees to be on the bottom. And some of you are like, oh, Miss Johnson, can I just multiply by pi over 180 instead? Absolutely. It's up to you. And then this one's just going to be a handstand of that. So 360 over 2 pi or 180 over pi. All right. So hopefully this makes sense. Practice those things. Again, I think I said this, but I will, for number 8, if you want to explain this in your exit ticket, you can actually do that for your flip grid. But thank you for listening. I hope you have a great day. Bye.